Good afternoon, everyone. Today, I'm excited to present our work Heimdall towards risk-aware network management outsourcing. So network management is now increasingly outsourced because it's cheaper than running it in-house. And according to market report, managed services market size is projected to reach over $300 billion by 2025. And this type of service is provided by many companies, including Verizon, Fujitsu, and IBM. But it also raises significant security concern. An area that widely adopting network management outsourcing is network configuration troubleshooting. But frequent troubleshooting in a risky workflow also incurs more incidents. Current workflow starts from an enterprise administrator creating a ticket, describing the issue in the network to a ticketing system. And a third-party technician often have direct access to the production network. Here, a wrongly issued privileged command may cause a significant network issue from ransomware injection to large-scale service outage. The problem is significant, so we need a risk-aware network management outsourcing. Targeting the configuration troubleshooting case, we set our goal as defining and calculating the risk of changes to the network and guarding the network through risk monitoring and response. For this case, our work adopts a threat model that users are not involved in network management. An enterprise administrator is trustworthy, while a third-party technician has expertise to solve the ticket, but could also be the adversarial one that incur network incidents. Here's the outline. First, let me introduce the inputs to different components in our risk-aware management framework. Risk definition. It is the key input to our risk assessment model, which quantitating the potential impact from a value perspective. Risk assessment, in addition to risk definition, also takes into the network configuration files and assets information to calculate the accurate impact of risk. Finally, the risk monitoring and response system will take into the risk response policy from enterprise, do real-time accumulation of risk, and enforce the policy. Okay, first, risk definition. So how do we define risk today? In many network products, they associate individual risk with individual commands. For example, a shutdown is more risky than a show. But it's not flexible, because the same command may imply different risks under various configurations. For example, in a core SPF area compared to an edged one. What's even worse is that it's rather coarse-grained. For example, in Cisco iOS product, they only support up to 16 privilege levels for commands. So we propose our asset-based quantitative risk model. Our founding principle is that the risk of an event is the probability of its occurrence times the value loss by its consequence. Here we define assets as instances with values. They are the primary concerns of an enterprise, including physical equipment and software. And recall the ticket in our motivation diagram. Its resolution can project to a series of events modifying network configurations. Now consider a ticket T. We define the conditional probability, PFS given T, that the probability at which an asset can be affected during resolving ticket. We calculate the risk of a ticket based on asset's value, or S-dot value. Then comes our definition formula. The risk of T is defined by the sum of all assets attached to a network of PFS given T times S-dot value. So now that we have the risk definition and a bunch of network configuration files, how do we accurately assess the risk of a ticket? Existing approaches doing token matching on configuration files can hardly capture precise consequence dependency, because they may falsely link different configuration blocks. For example, they can falsely link all interfaces within a router since they share the same OSPF protocol token. This can then spread exponentially to neighbor interfaces and result in a dense risk consequence graph, which is difficult to reason about. So here's our approach. We construct a dependency graph not only on text, but also leveraging data plane information. We also calculate the accurate consequence probability with multiple affecting factors, including preference order and root cause estimation. Finally, the risk monitoring and response system. With the computation output of risk assessment and the policy, how do our system decide how risky is a privileged command? Doing verification is difficult and not sound, because correctness is hard to specify. According to a study in SecGuru, that even in data center network, most firewall rules are redundant, not mentioning complicated routing policies. So our work tackled it in a more dynamic way. Heimdall includes a centralized reference monitor with risk and policy input to achieve fine-grained risk monitoring and access privilege management. Now, let's jump into the real workflow of Heimdall. Let's travel back to the time when the enterprise administrator creating a ticket in the ticketing system. We limit third-party technicians' direct access to the production network. The ticket is then fed into our risk assessment model together with network configuration files and asset information. The output, or the risk of a ticket, together with a risk response policy, is then flows into the risk monitoring and response system. It will hijack every command that a technician issued and only permit commands that are safe. Let's first dig into the detail of our risk assessment model, which is mainly responsible for calculating this PFS given T. First, we need to construct a risk dependency graph, or RDG, to see how assets are impacted through blocks. Given a network, an RDG will depict how making modification to a block can change its impact and eventually affect which set of assets. Recall that we propose our approach as construct risk dependency graph leveraging data plane information. In detail, we have a set of 5 rules covering different cases, but the key idea is to make causal link between configuration blocks that a route is established, broadcasted, or learned, instead of doing pure token matching. However, when resolving a ticket, most blocks are not even accessed at the end. How to model this? Here comes our first observation, that the order and range in which operators access configuration blocks can affect the likelihood of consequence. For example, if there's something wrong in the OSPF block on router R1, a novice technician may access many blocks before really fixing the problem, while an expert technician can quickly identify the problem and solve it. The key idea from this observation is that how operators diagnose and resolve a ticket can be abstracted as a preference order defined on configuration blocks in the RDG subgraph. And the expert technician before can now put the root cause block at a higher position in this total order. But how do we know which block is the root cause block to model such a technician? Here comes our second observation, that the root cause can only be educated guessed before really get resolved. The key idea from this observation is that our model also takes as input the root cause estimation computed using historical stats. We can definitely incorporate other estimation using fancy debugging tools or methods. Before moving on, let's put things together. Regarding the PFS given T, the risk dependency graph, preference order, and root cause estimation will together contribute to this conditional probability, with detailed decomposition of a formula stated in our paper. Now, here comes the last component in our workflow, the risk monitoring and response system. Its key role is to inspect every command, figuring out the affected block, and make a decision that whether the command should be permitted. The decision is supported by the risk response policy together with current accumulated risk. The current risk when granting access to modifying a block B is a accumulation of all risks for all B prime that is placed earlier in the preference order than B. And our system will refer to RRP to check if current risk exceeds certain threshold and perform corresponding action, such as alerting or stopping immediately. For efficient ticket resolving, our system RRP can also define the access granting batches, which will help the enterprise administrator to push the access granting workflow faster. Now let's look at some evaluation of Heimdall. We complete a comprehensive expert validation with 99 rounds of experiments within 41 hours, demonstrating that Heimdall is efficient for practical usage with only moderate time overhead on the privilege management workflow. And Heimdall can reduce its outsourcing risks effectively, that 92% of tasks are solved without extra risks than the root cause block only. We also study the accuracy of our risk assessment model by showing that the strawman approach, by doing purely token matching, can generate significant more false positive dependency links than us. We also conduct a comprehensive study of affecting factor of risks, including the block type, access order, and privilege granting granularity, and etc. They are discussed in our paper too. Finally, we study the system components performance of Heimdall. Our centralized reference monitor can process commands quickly at a negligible expense of only 4 to 5 milliseconds per command. And 86% of tasks incurs less than 10% overhead on the risk-aware privilege granting workflow. Regarding the RDG construction and computation, they can scale easily to hundreds of routers for a large backbone network, and all the computation time is proactive before bothering the technician when solving a ticket. To conclude, we present Heimdall towards risk-aware network management outsourcing. We demonstrate that it is possible to manage risks when outsourcing network management. And we tackle the challenge figuring out and dealing with all the inputs by answering the questions include what risk is associated with resolving a ticket, and changes to word configuration blocks can potentially pose the greatest risk. And finally, how to automatically enforce risk response policies. If you are interested, you are more than welcome to read our paper for further detail and demonstration. And we also invite you to extend our work by utilizing our risk assessment techniques in other network and system scenarios. Thank you, and I'm happy to take any question.
Questions? Right, while other folks are thinking of questions, I have a question.
Okay.
So my intuition is that for your risk scores for these different operations, that they're going to be pretty similar to each other. That like once you start messing with configuration for a router, like even some of those, blocks tied to one specific interface, like that interface has a lot of cascading consequences. So I guess my question is, do you see dramatic score differences between different operations, or do they all basically impact the whole network?
Okay, we will see, your concern is reasonable. Like, for example, we do observe patterns that, the first several malicious blocks in the network can, with only one block, can cause, significant risk score in our network. However, we do see that in certain cases, for example, at some, access network or the access interfaces issues, the technician can resolve them, only playing with the edge interfaces that incurs less risk. Thank you.
Okay, thank you. Any other questions? No? Let's thank our speaker again.